most of our homes, we see the fan that works in our home, the electric dryer, the driller. Most of the things are made using a motor. Motor is incorporated in most of the things that you use in your home, like the washing machine. They all have electric motor. Okay, electric motor. They drive the turning, that force, that motion. You plug the washing machine, and then the motor drives it and creates the spin. That spinning that washes the clothes is the effect of electric motor. So how is the motor designed? What happens in the case of motor? Where do we start from? First and foremost, the first thing we know is that if you take a wire, anytime we take a wire, okay, let's take a look at this one. When you take a wire, let's say a conductor, you take a conductor, let's say this is a basic conductor, a wire, okay? Anytime current flows through this conductor, magnetic field will be produced around the conductor. Magnetic field will be produced around the conductor. You know, if you have a straight line wire, is called a wire, right? A straight line conductor is a wire. If you fold it twice, it becomes a coil. If you fold it like this, it becomes a coil. If you make it many times, it becomes solenoid. Please take note. So when we say wire, coil, solenoid, sometimes we may be referring to the same thing. So this is coil, this is a coil, and this is a wire. They are all conductors, okay? They conduct electricity. This is a wire, this is a coil, and this is solenoid. Solenoid, okay? Okay. Now, our first establishment is that whenever we take a wire, we allow currents to flow through this wire. I can use wire and conductor interchangeably. Okay, how do current flows through this wire? Is if I connect to a battery, right? Let's say I make a battery here. I make a battery. Then that means current will flow through this conductor. Current will flow through this conductor. This is the longer arm. Remember, the longer arm is the positive side of the battery. So always watch out for the positive and the negative side. So wherever the positive is, that's where the current will start to flow. That's the direction current flows through. So meaning current will be flowing in this manner. It will be flowing upward this way. Current will flow like this, and then in this way it will be going down because the current will flow in this manner. So whenever, this is a wire, this is a conductor, okay, this is our wire. Whenever we have a wire or a conductor, and if current flows through it, circular magnetic field will be produced. So the magnetic field will be in circular form like this. Okay, they will be oriented like this. Okay, magnetic field will be produced around the wire, around the conductor. So this is where the motor effect is derived from. This is where the motor effect is. So magnetic field will be produced anti-clockwise. Okay, magnetic field will be produced in this manner anti-clockwise, circling around the conductor, So that's the first notion. There, remember the motor. Anytime we are building a motor, we need a magnet. We need magnets. So if I take two magnets, let's say one is characterized as a north pole, and the other magnet is characterized as a south pole. Then this magnet will also produce what? Let's say this is our north pole, and this is our south pole. The magnet will also produce magnetic field. The magnet will also produce what? Magnetic field. Remember, we say whenever current flows through a wire, it produces a magnetic field. We showed this first one. In the case of current carry, wire carry current, or a current carry wire, okay? So we say magnetic fields are produced here. Then, when we bring magnetic field are also by default. This one is by default. Magnetic fields are produced from the north pole to the south pole. Magnetic fields are produced whenever we have two magnets, north and south. Magnetic field will be produced. Magnetic field will be produced from the north to the south. The field, even though they are imaginary, you don't see them, but it's kind of a force that is created. There's a force existing between these two magnets. That's what we are saying. So magnetic field is produced within two magnets, north and south. So now, what will then happen if I bring this wire between this north and south? What will now happen? We bring this conductor between north and south. So you know, originally there is magnetic field in the wire, and again there's magnetic field between the two the two magnets. There's a magnetic field between the two magnets. So there will be two magnetic fields if I bring the conductor here between the North Pole and the South Pole. Okay, especially if I connect it to a battery. If I connect it to a battery, there will be what? There will be, if we connect this to a battery, there will be, this is how you make a simple motor. If you want to make silicon yourself, you can do it. This is the basic principle. But we're going to show you how to make it a better one. Okay, so now if we put a battery here, it means this is the positive. The longer arm is the positive, and the lower arm is the negative. It means current flows in this manner. Current will start to flow in this direction. Current flows in this direction, right? Current starts to go up this way, and then it goes like this, and then it comes like this. So during this place, the current is flowing down. So here, there is two magnetic fields. The magnetic field between the North Pole and the South Pole of the magnet, and the magnetic field on the conductor. The magnetic field on the conductor, the circular magnetic field on the conductor. Well, you know, we say whenever current flows through a conductor, magnetic fields are produced around the conductor. So, which means every wire you plug in your house, every wire, if you peel the insulator, if you remove the insulator, okay, because of the insulator, you don't feel it. You insulate it with the insulator. If you remove the insulator, if it's a pure conductor, like a pure conductor, where you remove the insulator, magnetic fields are produced around the wire itself. And there's another magnetic field from the North Pole to the South Pole of the magnet, meaning there are two magnetic fields in this region alone. There are two magnetic fields in this region alone. So these two magnetic fields, they will start to interact. The word interact. The two magnetic fields will interact. The two magnetic fields will interact with each other. And so, when they interact, they will create a force. They will create what? A force. This is the principle of motor. They will create a force. The two magnetic fields will interact. You see, the two magnetic fields, where are the two magnetic fields? Where is the two magnetic fields coming from? One is coming from the magnet, the North Pole and the South Pole. That's magnetic field moving from the North Pole to the South Pole. The second one is the circular magnetic field that is always around a conductor. The circular magnetic field that is always around a conductor whenever current flows through a conductor. So there are two magnetic fields here taking place. Now, these two magnetic fields, they will interact. This is what they will interact. So when they interact, they will create a force. They will create a force. Okay, the direction of the force is not depending on the Fleming's left-hand rule. Okay, so if you look at the Fleming's left-hand rule, when the current is your first finger, I'm going to show the Fleming's left-hand rule later when I'm explaining. When we go to the motor itself, the electric motor structure itself. So your first finger is the direction of the magnetic field from the North Pole and the South Pole. Okay, your first finger. Your second finger is the direction of the current, meaning current will be flowing down, like in this case now current is flowing down, and the magnetic field is moving from the North Pole to the South Pole. If you arrange the polarity like this, the north is this way, the south is this way. But if you change the polarity, the direction of the force will change. In this case, in this particular case, the force will be the thumb, the motion or the movement. The movement is the force, and it will be the direction of your thumb, your finger thumb, okay, the top of your finger. So that your thumb will be going up if you do Fleming's left-hand rule. So this thumb is representing the force or thrust. Force or thrust. T-H-R-U-S-T. Thrust or force or movement. Okay? So which will cause rotation. Later on. But the first case, you just need to know that this one will move up. This wire will move up, will jack up. This entire wire conductor will jack up. That's the first principle, what we need to know in a current carrying conductor placed in a magnetic field, in a magnet placed between two magnets. Current carrying conductor, a current carrying conductor placed between magnets. So we create a force. Okay, if the rotation is like this, the force will move up. But if the current is flowing in the opposite direction, the force will go down. If the current is going like this way, if you reverse the direction of the current, the force will go down. If you change the polarity of the battery, the force will also go down. The polarity of the magnet. That means you put south here, you put north here, the force will also go down. If you change the polarity of the battery, the force will also go down. So these are two factors that can reverse the direction of the force, that can change the direction of motion or rotation, as the case may be. Now let's go to, these are the basics to understand the electric motor. This, what I've just explained, if you understand it, it means that you understand the electric motor, how it works, okay? So the first thing, like I said in an overview, is that the force, whenever you have a conductor and a current is flowing through it, circular magnetic field will be produced around that conductor. That's the first thing. The second thing is that if you bring a magnet, north pole and south pole of a magnet, the magnetic field will be produced moving from the north pole to the south pole. Now, the third step is if you now bring the conductor between the poles, the north pole and the south pole, then there will be two magnetic fields. There will be two magnetic fields. The first one will be the one from the magnet, moving from the north pole to the south pole. The second magnetic field will be around the conductor itself, circular magnetic field around. Then the two magnetic fields will interact. This word is very important. They will interact. They will start to talk to each other, communicate, interact, and create a force. That interaction is what creates the force. Because in the exam, they can ask you what creates the force or the thrust. The force can be called the thrust. The interaction creates the force or thrust or movement. So whichever word the textbook uses, the force or thrust or movement or motion, whichever word any given textbook decide to use, is the same thing, it's the same context, okay? Force, thrust, motion, movement, it's okay, same thing. Okay, so if we understand this, then we can now go to the electric motor proper. So we say the motor effect, this is called the motor effect. This is called the motor effect. This is the principle of electric motor. This is how it starts. This is the principle we lay down to build the simple electric motor. So the motor effect can be used to create a simple DC electric motor. So if we want to create a DC electric motor, we can do this, okay? Now the force on the current carry coil, this is the conductor. The current carry coil is the conductor. Can cause a rotation to happen, can cause movement to happen, can cause rotation or movement. But that's the case of electric motor. But this is the simple foundation of electric motor. Now let's go to electric motor itself. A simple motor, what is it comprised of? Electric motor. When you hear of electric motor, what is it comprised of? The first thing it comprises of is a rectangular array of coil. Rectangular array of coil. So instead of just one conductor, a straight conductor, we make a rectangular coil. We make a rectangular coil between the north pole and the south pole of a magnet. We make not just a straight conductor this time around, we make a rectangular array of coil. We make the coil to be in rectangular form. Is that okay? So a simple DC electric motor consists of a coil of wire that can rotate because of the motion created on this side and on this side. Because maybe if a force is jerking this up, a force is jerking this side up, it will cause rotation. Force is pulling one side up, another force is pulling the other side up. A rotation will begin, the rectangular array will begin to rotate. The rectangular array will begin to rotate. So before I continue this, let's take a listen to the tutorial, and then we come back and I will explain the details of this to you very well. Okay? Now let's take a look at this tutorial. Okay?
Right, here's a question for us to have a look at, and we'll start as usual by reading through the question carefully. The diagram below shows a simple DC electric motor which is rotating. Identify which parameters should be changed to make the motor rotate more quickly. So here's our DC motor, which is just a coil inside a magnetic field. So there's a north pole on this magnet, a south pole on this magnet. So my field is running from north to south, it's running in that direction. This coil is rotating, and it's rotating because there's an electromagnetic force being developed. And you'll see that I've got a positive current going in there, negative coming out there. my current by convention flows from positive to negative. So this coil has an electromotive force being applied to it, which is causing it to rotate. The question is, which parameter, and I'm given a whole bunch of choices below there, must I change to make it rotate more quickly? So to make it rotate more quickly, I need to increase the force, the EMF, that's being developed. So we're going to answer this one by exclusion and then also answer it using some of the theory we know. So just two methods of answering this question. So increase the number of turns of the coil. That looks like a reasonably good answer, so I'm going to leave that one for now. Let's look at the second one, remove the magnets. So the electromotive force is being developed because of induction, electromagnetic induction. If I take away the magnets, I'm removing the magnetic field. If I remove the magnetic field, that coil is not going to move because I no longer have electromagnetic induction. So that is absolute nonsense. It's definitely not going to speed up if I remove the magnets, and contrary, it's going to slow down and it will actually just stop. Reverse the terminals of the power supply. So in other words, what this choice is saying is make that one the negative, make that one the positive. I'm hoping you can intuitively see that if I change the terminals of the power supply, this is not going to speed up. It's actually just going to rotate in the opposite direction because I'm changing the direction of the current. Similarly, if I reverse the polarity of the magnet, so if I make that a north and that a south, I no longer have an magnetic field running in that direction, left to right. I'm now running it right to left, so that will also not speed up the coil. That will just actually cause it to change direction. It'll rotate in the opposite direction. So by exclusion, I've got this increasing the number of turns of the coil. So we're going with that as our correct answer, but we've solved it by exclusion. If you do remember the theory, and I'm going to bring up the screen grab, here it is here. Remember the force applied by the motor, that's the EMF, the electromotive force. That is a function, or that can be increased by increasing the current in the coil. In other words, just putting more current through these two, through the power supply. Increasing the strength of the magnetic fields, so just using bigger magnets or magnets made of different materials that perhaps have a stronger magnetic field, or by adding more turns to the coil. Now, I'm not given those two options, but I am given that as an option. So to make it rotate more quickly, you need to link that to increasing the EMF, the electromotive force. And the force can be increased by adding more turns to the coil. So our first option in this case is the correct answer.
Hello, okay, so that's just for a question. This was not a full tutorial, it was just for a question, okay? So just for a question, a single question. However, the video didn't explain what the whole thing we wanted. However, it's okay. Now let's go and do what we know how to do best. Now let's come back to our electric motor. We come back to our electric motor. The video was just asking if you want to increase the force produced, that force of rotation produced. He gave an option, what can you do to increase the force? The only correct option was to increase the number of turns here, because we're going to describe that. To increase the force produced or to increase the rotation, you have to increase the number of turns. That's one. Number two is to use stronger magnets. Number three is to use a stronger battery. Increase the cell of the battery. Increase the cells of the battery. So these are three things you can do to increase the force produced or to increase the rotation of this coil. Okay? So that's what the question handled. Now let's take a look at this. Here we have a simple DC motor. Now this simple DC motor is comprised of a rectangular array of coils, and it's made up of also permanent magnets, north and south, and it's made up of slip ring. The coil terminates in the coil, in the split ring commutator. Remember, this split ring commutator is a conductor. Okay, it's also rotating with this one. As this one is rotating, the slip ring is rotating. Okay, so when it's at 90 degree, then this open side, it has open end here, will be touching the side of the carbon brushes, which is connected to the battery. At that point, there will be no current flowing. Only the torque will keep the rotation going. Okay, till it reverses the direction. Okay, we're going to talk about that. Then these are carbon brushes to protect us from touching any of this conductor. Okay, so this is a simple DC electric motor. This is how it looks like, meaning you need a battery, you need a rectangular array of coil, you make the coil rectangle, you need slip ring, and you need the carbon brushes, and you need batteries. These are the things you need to build a simple electric motor. These are the things you need, okay? Now, as current flow through the coil, it will produce what? As current flow through the coil, it will produce what? Magnetic field. The coil, I've already explained this from the beginning, that whenever current flows through a conductor, magnetic field will be produced, circular magnetic field will be produced around the conductor. So as current is flowing through this conductor, magnetic field will be produced here. Okay, here, for this one, magnetic fields are produced from the North Pole to the South Pole. We don't need to draw that, we already know that. We can show it like this, North Pole to South Pole. Okay, even though you don't see that like they are imaginary, from North Pole to South Pole, magnetic fields are produced. From North Pole to South Pole, from North Pole to South Pole, like these magnetic fields are produced. And also around here, magnetic field is produced in this conductor. Around here, circular magnetic field is produced here. Circular magnetic field is also produced here. Here, even though magnetic field is produced here, but there will be no force produced in this side. Why? Because the magnet is not in this side. There will be no interaction with the magnetic field here and the one here. The only interaction is the magnetic field around here and that of the magnet, and the one around here and that of the magnet, which will cause the motion. So we can erase this one. I only show you so that you can see. We can remove this one. Now the force for this particular one, the current is going up this way. The current is going up. So we're going to use Fleming's left-hand rule. In Fleming's left-hand rule, if you hold your left hand, your first finger, we only need 3 fingers, your thumb, your first finger, and your second finger. Your thumb, your first, which I'm going to show. I'm going to show Fleming's left-hand rule, this one. Okay, you're going to hold your thumb. This is your thumb. This is your first finger, and this is your second finger. Okay. Now each of them, they are 90 degrees. This one is 90 degrees. This one is 90 degrees to this one, even though it doesn't look it, but it's actually 90 degrees. And this one, they are also 90 degrees. Each of them, they are 90 degrees. If you do your finger, you will know that they are all 90 degrees. This one is 90 degrees to this, and this one is also 90 degrees to this one. This first finger and second finger, they are 90 degrees, and the thumb and the first finger, they are also 90 degrees. Now, in Fleming's left-hand rule, it says whenever the magnetic field, meaning the North Pole is here, if I put a North Pole here, and I put a South Pole of magnet here, meaning the magnetic field are going from this way to this way, from the left to the right, magnetic field are going from the left, and the current is flowing down. Your second finger is the direction of the current. Your second finger is the direction of the current. Your first finger is the direction of the magnetic field. So the current is flowing downward. The force produced will be upward. The force is called the thrust or motion. Will be upward. So if we go back to this motor, the one we are showing, let's take a look at this. In this motor, this first one, if we use the Fleming's left-hand rule, you can see that current is flowing this way upward. Current is flowing up. Let's take a look at current is flowing up. So current, because current is positive is where current shows the direction where the current starts to go in. So current going through this, it enters this split ring commutator, then the coils are connected to this split ring commutator, and then it continues to flow like this. So in this direction, current is flowing up this way. The current is going up this way, and it's going this way. In this way, it's going down. This way, the current is going down. Okay, now let's take a look at what will happen here. If the current is flowing, in the Fleming's left hand, the current is flowing down, right, in the first case. But you have to twist your finger. If your current is going up instead of down, it's going up, and this one is still in the north pole. This one is still north to south. From left to right, north to south is left to right. Then the force will not go up. See, the force will go down. This force will go down. Because we have to twist our finger this time around. We have to twist it like this. You have to twist your finger upward in an upward manner. So the force will go down. So here, the force produced will act downwards. The force produced will act downward. There will be a downward force. I think we should use a different color for this. The force produced will act downward here. Why? Because the current is flowing up. Normally in Fleming's left-hand rule, current is supposed to flow down. So when the current is flowing, like here, this way, current is flowing down. If you look at this way, current is flowing down. This way we follow the normal Fleming's left-hand rule. And here is the north pole to south pole, left to right. North, left to right, north pole to south pole. That's the direction of the magnetic field. This is the direction of your first finger, the direction of the magnetic field. So since the magnetic field is from the left to right, and current is flowing down by your second finger, then the force, the thrust, or the force, or the motion, whatever you want to call it, here it will go upward. The thrust, or movement, or motion, or force will act upward. The force acting on this coil, the electromotive force acting on this coil will be upward. The motion, the movement. Meaning what it means is because there will be a movement, upward movement, this one will rotate up. So this one is going down, this one is going up, we cause what we call rotation. So the whole coil will rotate. The whole coil will start to rotate because the force is pulling this side up, a force is pulling this side down. A force is pulling this side up, and a force is pulling this side down. So it will cause a rotation. This rectangular disc will continue to rotate. So this is the motor effect. This is the effect of electric motor. This is the effect of electric motor. So once again, we say we use the Fleming's left-hand rule to explain the electric motor. We use the Fleming's left-hand rule to explain the electric motor. And we said whenever we have our north from the left, our south is on the right, that means the polarity is arranged like this. Our first finger, this one, will be the direction of the magnetic field. This first finger. The second finger will be the direction of the current. Each of these three fingers, they are 90 degrees to each other. So if they are parallel, there will be no force produced. There will be no effect. If they are parallel, you must make them 90 degrees to each other. They must be 90 degrees to each other in order for this to hold. In order for electromagnetic induction to happen, for EMF to be reduced, or for a force to be produced, in this regard. Okay, so that's that for that. So when the north pole is on the left and the south pole is on the right, magnetic field is moving from the left to the right. And if the current is going down, according to Fleming's left-hand rule, the second finger, the current is going down, the force will act upward. Always remember that the force will act upward. Now, if the current is now going up, the force will be opposite. The force or thrust will act downward. And this will cause a rotation. This will cause this rectangular coil to be rotating between these magnets. And we say the split ring commutator will rotate alongside with it. You see, we create space here and space here. So that when it's at 90 degree, there will be no contact. With the carbon brush. There will be no contact. It will be empty space. There will be no contact. So there will be no more current flowing. But it will still rotate because of what we call torque. There's what we call torque in physics. Okay? If a high force, it's just like you paddle a bicycle. You paddle a bicycle for a long time or for some time. Even if you stop paddling, your bicycle will keep moving. That's what we are saying. So even if it's at 90 degrees, where there is no contact, it will keep rotating because of torque. because of torque that is already created, the kind of force that has already been created, will continue to make it to rotate. Now let's move on quickly. Now let's take a look at the operation of the electric motor. First of all, what's the difference between electric motor and an AC generator? A DC electric motor and an AC generator. In the case of motor, we use electricity to create force. Electricity is used, in the case of motor, we use what? Electricity to create, electricity or electrical energy is used to create what? Force. Force is a mechanical energy. So you can say electrical energy to mechanical energy. You can say electricity to create force. Electricity is an electrical energy and force is a mechanical energy. So someone can say in a motor, electrical energy is converted to mechanical energy. You can find this in multiple choice exam question. Okay? You can find this in multiple choice question. In the case of electric motor, electrical energy is converted to what? To mechanical. Or they may say electricity is converted to force or thrust. So electrical energy is converted to mechanical energy in electric motor. In the case of generator, in the case of an AC generator, so I just write AC. I just write a generator. Motor is a DC because we are using battery. A DC is from battery and AC is from your power source in your home. Okay? Generator. If you have a generator, what do you convert? You are converting a force Okay, in the case of a generator, we are converting what? We are converting a force or thrust or motion or movement into what? Electrical energy. Into electrical energy or into electricity. Into electric. Okay, for short I'll just write electric. Okay, into electrical energy. So you must know the difference. They are like vice versa. They are like vice versa. Generator convert mechanical energy, let me write ME, mechanical energy into electrical energy, EE. That's a generator, EE. Motor convert electrical energy, EE, into a mechanical energy. Motor convert electrical energy into a mechanical energy. Okay, so into a mechanical energy. Okay, like in the case of your washing machine, you plug it. When you plug it, it gets electrical energy, and that electrical energy is used to speed, to cause spinning, which is mechanical, to create motion, which is mechanical energy. Okay, so that's what you need to know. Now, the basic point we need to summarize here is that if the effect of increasing or the turning effect is increased by what? If I want this one to rotate more, if we want this rectangular array to rotate more, what are we supposed to do? The turning effect. If we want it to be more, what do we need to do? We have, number one, we have to increase the number of turns. We have to increase the number of turns. We have to increase the speed. The number of turns we have to increase. By increasing what? One, you have to increase the number of turns of the coil. Number of turns on the coils, you have to increase. You have to increase the strength of the battery. You know the battery is the one producing the current. You have to use a bigger battery, a stronger battery. And then you have to use a bigger or stronger magnet to create a stronger magnetic field. You have to use a stronger magnet. You have to use a stronger magnet, okay, to create a stronger magnetic field. Is that okay? So these are three things. Anytime you want to increase the turning effect, these are the three things we need to do. In order to increase the turning effect, we have to what? Increase the number of turns on the coil. We have to use a stronger magnet to increase the current on the coil. We have to use a stronger magnet. Here we have to use a stronger battery. Here is a stronger magnet to increase the strength of the magnetic field. Okay, now let's move on to the operation of a DC electric motor. This is for extended student. So if you are not an extended student, you're not doing physics in IGCSE paper 4, I think the basic knowledge is enough for you. Now, for extended students, let's take a look at what's happening, although we have already summarized it. In a DC motor, when the coil of the wire is horizontal, this is when the coil is horizontal. You can see the horizontal coil. Okay, the arrangement is horizontal. Now, when it's horizontal, it forms a complete circuit with a cell, right? Because, why is it a complete circuit? Because you connect to a cell or a battery. You connect it to a cell. This is the carbon brush. This is the carbon brush, okay, to insulate you from because this is a conductor. To insulate this split ring, this one, you can see the split ring. You can see the space between them. There's really a space. So when it rotates at 90 degrees, this space will face the carbon brush, which means there will be no contact. When there's no contact, there's no more current flowing to the circuit. There will still be rotation because of the torque. I already explained that, right? Now, if you take a look at this, the current is going this way. For this particular circuit, the current flows in from this is the positive arm of the battery. This is the positive arm. Current always flow into a circuit from the positive side. Okay? Current flows through this way, goes in here through these carbon brushes that insulates us from or protect us from this split ring, which is a conductor. The rectangular array of the coil are connected. They are in contact with this split ring, which means the split ring is also rotating with this rectangular array of coil. This split ring, they are also rotating. So the current flows through this split ring to the coil, and then here on this way. Now on this way, when the current is here, when it has reached this place, there are two things. We already say magnetic field is created here, right? Magnetic field is created around a conductor carrying current. Okay, created here. And there's also a magnetic field coming from the north pole of the bar magnet to the south pole. So the interaction between two magnetic fields, you must remember this. The interaction between the two magnetic fields create the force. Now the direction of the force will be determined by the Fleming's left-hand rule. Now since the current is going, the left-hand rule, when current is flowing downward by the second finger, the force will go up. But in this case, here, the current is not flowing down, it's flowing up. The current is flowing up. Since the current is flowing up, meaning the force will go down. Meaning you can twist your finger. The current is now flowing up, not down. The current is flowing up, the force will go down. The force is going down. Okay? The polarity of the magnet is still the same. From north on the left, south on the right, still the same. So since the current is flowing up, the force acting here will go down. The force acting here will go down. The force will act downwards here. The force acting here will go down. Okay, I may draw, let me erase. Let me show you where. Okay, the force acting here will go down here. The force acting will go down. Okay, as shown like this. Okay, as shown like this. So the current flows this way. Now, why is it that there's no effect here? Because the magnet is not placed here. And moreover, this is parallel. Here is parallel to the direction of the magnetic field. The magnetic field, they're here like this. North to south, they're here. Okay? They're here, north to south. Okay? They're here, north to south. So, since the magnetic fields are like this, north to south, when current is flowing, it's parallel. Parallel current parallel to magnetic field does not create any force. Because the question why is it nothing happens here when the current is flowing here? Because the current's direction is parallel to the direction of the magnetic field. So since it's parallel, there's nothing that is going to be happening. There's no interaction also, mind you. So, but when the direction it reaches here, it starts going down. When it's going down, okay, it's now 90 degrees. See, the current is 90 degrees to the magnetic field. The current, when it's going down here, is 90 degrees to the magnetic field. According to Fleming's left-hand rule, when the current is going down and the north pole from left to right, north on the left, right, south pole on the right, magnetic field, if you hold your left finger at 90 degrees between the thumb and the first finger and the second finger, then the current is flowing downward, the force will act upward. So there will be a magnetic force or motion that is acting upward here from here. So these two will cause a rotation. This one is pulling this rectangular array up. This one is pulling it down. So it will cause a rotation. And that rotation will be along with the split ring commutator. They will all both be rotating. Both the rectangular array will be rotating and the split ring commutator will be rotating. So when it reaches 90 degrees, when it has rotated 90 degrees, there will be no contact between, because this part will be touching the carbon brush at this point, and also on this side. There's also a carbon brush here that you don't see because of the way the diagram is drawn. So, but the rotation will continue because it's, so when it reaches 180, the direction of rotation will reverse. We'll talk about that, okay? Now let's move on. Now we say, let's take a look at the theory. Say the current flowing through the coil produces a magnetic field. We already know that. Whenever current flows through a coil, it will produce magnetic field. And also the magnet also produces magnetic field. There will be interaction between these two magnetic fields. The one on the current and the one on the current, magnetic field on the current, the circular magnetic field on this current, and the left to right magnetic field by the magnet. So that interaction creates the force. We already talked about that. The direction of the force will be determined by your Fleming's left-hand rule. Okay, so once you understand that, we are good to go. We are good to go, right? We said this magnetic field, they interact with the uniform external field. So a force is created. What's the uniform external field? Is the one from the magnet. Is the one from the magnet. The magnet itself produces magnetic field because you have a north pole and south pole. The magnet itself is the external magnetic field. And then the current carry wire also produces magnetic field. These two fields interact with each other. The two fields interact with each other to create a force. To create a force. The force or thrust or movement or motion is going to happen on both sides of the rectangular array of coils. It's going to happen on both sides, and when that happens, it will cause rotation of this rectangular array together with the slip ring commutator. They will all be rotating, except this carbon brush. This one will rotate alongside with the rectangular array, creating a motion, a force. Okay, that's how electric current creates a force in electric motor. That's how electric current creates a force in electric motor. Now the force act in the opposite direction on each other on the coil. Yes, opposite direction. The force here will be acting downward. The force here will be acting upward, so that it can create rotation. So that this coil will be able to rotate. They might ask you, why is it in multiple choice? Why is it that the force are acting in opposite direction? The force created on the rectangular array of coil, why are they in opposite direction? So that it can create rotation on the field, on the coils. Okay. Now, so we've already used Faraday's law. I've already explained the Fleming's left-hand rule, to show where and where this rotation will happen. Now, when it rotates and the rectangular array of the coil is now vertical, the coil is now in the vertical position, it's no more in the horizontal position. Because as it's rotating, just like you take your phone, you make it horizontal. Okay, your phone. You take your phone like a rectangular coil. When it rotates 90 degrees, it will be vertical. When it rotates 90 degrees, it will be vertical. Now, when it's now vertical, you can see the empty space between the split ring, between the two split ring. The empty space is now facing the carbon brush here. Also, the empty space here will be facing the carbon brush on this side. Okay, it's because of the drawing. Okay, that you're not seeing that this one is directly here. They don't want to put it inside here so that the drawing will make sense. But it's actually facing this empty space, and this one is facing this empty space. There's no more contact. There's no more contact between this carbon brush from the wire. You know, the wire goes through the carbon brush. Okay, there's no more. The wire goes through. You create a hole on the carbon brush, the wire goes through, and it's connected to this slip ring commutator. So here there's no contact. There's no direct contact here. So current is not easily flowing at this junction. So what happens is the torque. What keeps the rotation is the torque. We're going to show a graph to demonstrate this effect. Now, no force acts on the coil when vertical, as the split ring is not in contact with the brush. No force is created here. No force is created to cause rotation to happen. But the rotation will still happen, however. The rotation will still happen because of the torque. They might ask in the exam, what at 90 degrees or when the coil is vertical, there is no force created at that point to cause rotation. What keeps the rotation going? What then keeps the rotation going? The rotation is kept going with the torque. Okay, I use the bicycle to do example. I say if you paddle a bicycle and ride for a while, if you stop paddling, the bicycle will still be running even if you're no more pedaling. Even if you are no more pedaling, the bicycle will still be running. So why? Because of this force. There's a force called torque. Torque is a force that will keep it rotating. So even if there's no contact, there's no current at this point, because of this empty space, there's no force produced to cause rotation. It will still rotate, however. It will still rotate because of the torque. Okay? Now, this is what is explained here. Even though no force acts, the momentum of the coil, the momentum, that's the torque. The momentum is the torque. Okay? So you may use the torque or you use the word momentum. The momentum of the coil causes the coil to continue to rotate slightly. But it's not a strong one. It's not like you're paddling. It's just like you stop paddling, the momentum will still keep going. The bicycle will still keep running. Okay? But not as fast as when you are paddling. Okay? So it will keep slightly so that it can pass that face. So that it will rotate to pass it and put it back in the horizontal. To put the rectangular coil back in the horizontal orientation. Is that okay? Now the slip ring reconnect with the carbon brush and current start to flow again. So when you keep rotating, the momentum, keep it, or the torque. So you say torque or momentum. Any word you want to use is fine. In the Cambridge IGCSE, I think they will use the word momentum mostly. Okay? They will be more familiar with the word momentum. So when you get to higher level like A level or university, they will be using more of the word torque. Okay, so the momentum, we keep this one rotating. We keep it rotating till it's back to its rectangular, its horizontal form. Till it's back to its horizontal form. When it's in horizontal form, this slip ring will be here. And this other one will be on this other side. And then there will be contact and current will start to flow again and rotation will continue. Rotation will continue. Is that okay? Okay, so that's now the current still flow towards the cell on the left and away from the coil. Okay, these are just a lot of explanation. Now let's take a look at this. The force on the coil when rotated 180 degree. Now when it has rotated 180, this blue one was here originally. Rotation has brought it this way. Okay, and this, see, it has, the split ring has changed hand. The one that was here is now here. The one that was here is now here. Originally, maybe if you look very well, you see the blue one was here. The blue one was here. Why we change the color so you can understand. So at 180, it has become this. It has become this. This is 90, this is 180. The blue is now this way. So meaning, if I show it in a graph, this is 180 degree rotation. The first one is here. Okay, the second one is here. Second half is here. Okay, the first one, 90 degree, I think 90 degrees here, right? And 180 is here. 180 is here. Okay, beyond 180, you are going back, right? Okay, so you are going back to the original form. So this wire we twist. The blue one that was here, we twist this way. And the red one, and the black one that was this way, will be this way. This is what we see earlier on. Look at it. The blue one was here, and the force was up this way and down this way. Now, it has rotated 180 degree. Here is at 90 degree. This one is at 90 degree rotation. 90 degree rotation. And then here is at 180 degree rotation. So at 180 degree rotation, the force here is down. The force here is up. Current is going, okay, because it will change, right? Right? Here was up and here was down. Okay. The direction of rotation is still the same. Direction of rotation is still the same because polarity is the same and the direction of flow of the current is the same. So the force here is still going down, the force here is still going up. So rotation will continue. This rotation will continue. Okay. So this is the basic principle of an electric motor. Now let's take a look at the factor affecting the DC motor. What are the factors? So one of the factors, I've already explained them. I say if you want the speed to increase, the speed at which the coil rotates can be increased by what? If you want to increase the speed, one of the things you have to make more coils. You increase the number of turns here. Okay, you make more turns. If you use 500, you can make it 1000 coil. So you can increase the torque to increase the speed of rotation. That's number one. Number two is you can make the battery and the magnet a thicker one. You can make it a thicker magnet. Okay, something thicker, like the one we had at the beginning. Look at the beginning one. Something very thick. The one we had at the beginning, you see, is a thicker one. This one is way thicker. So if you want to increase and even the coil here, they're more than the other one. So you can see, you increase the thickness of the magnet. You make a thicker magnet, it will increase the speed of rotation. It will increase the speed of rotation. So, and also the battery. You increase the strength of the battery. The battery you are using, if it's 1.5, you can increase to a volt, or if it's 6 volt, you can increase to 12. If it's 12, you can increase to 24. If it's 24, you can. So you increase the strength of the battery, you will increase the speed of rotation. So the strength of the battery and the strength of the magnet, and another one is the coil, increasing the coil. Now, if you want to change the direction of rotation, if you want to change the direction of rotation, what do you need to do? If you want to change the direction of rotation, what are we supposed to do? You change the polarity. See, if you want to change the direction of rotation, you can change the polarity of the magnet. Take this south, put it here. Take the north, put it here. Once you do that, the direction of the force will reverse. This force that was going down will go up. It will now be Fleming left hand rule, but you will have to twist your hand to the right side. You have to twist your hand to the right side. Okay? So it will change the direction of rotation. That side that was going down, if I bring this north here, south here, meaning the magnetic field will be going from right to left, no more left to right. So this one we act upward. The force here will start to act upward, and the force here will start to go down. Only doing that alone, we change the direction of rotation. That's one. Number two, to change the direction of rotation, you change the polarity of the battery. Put the negative here, put the positive here. So the current will start to flow this way. If you do that, this force also will start to act downward, and this one will start to act upward. So these two things, if you want to change, these are the two things you need to do. If you want to change the direction of rotation of the coil, change the polarity of the magnet, or change the polarity of the battery. These are the two things you need to do, and then that will be done. Now let's take a look at the question. See, he said, if you want to change the direction of rotation, what are the things you need to do? One, you reverse the direction of the current supply, and two, you reverse the direction of the magnetic field by reversing the pole of the magnet. Okay? The force supplied by the motor can be increased. If you want to increase the force supplied by the motor, what do you need to do? You have to increase the number of turns. You have to increase the strength of the magnet, so that it will create more magnetic field, greater magnetic field, and then you have to add more turns. Okay, you have to increase the current by increasing the battery size, and that's number one. Number two, battery size, increase it so that more current will flow. Number two, increase the strength of the magnet by using stronger magnet, so that the strength of the magnetic field will be more. And then number three, add more turns of the coil, more turns of coil. Okay, now let's take a look at an example. You have, a SIPO DC setup is shown below. You have a SIPO DC, you have the north pole, you have the south pole. Okay, you see the polarity is not left to right now, it's right to left. So even though current is flowing this way, now Fleming's left hand rule, you have to reverse. Normally, if here was a north pole and south pole, then we see. Now let's take a look at what the question wants from us first. Let's see. Okay. It said determine whether the coil will be rotating clockwise or anti-clockwise. This one could be an exam question, whether it will rotate clockwise or anti-clockwise. First of all, where will the direction of the magnetic field be? magnetic field will be from right to left. Why? Because we put the north pole here and we put the south pole here. That's the first thing you see. So if you follow left, this is now the opposite in the Flemish left hand rule. This is the opposite, meaning we have to make our hand to make the finger start going from left to right. Okay? And the current start to flow up. If the current start to flow up, look at it, because this is the positive side of the battery and this is the negative side of the battery. So here from this side, the current start to flow up from this side. Current will go up here, and here current will go down. Okay, like as you see here, see current is going up here, and here current is going down. This is how we begin. So we've established this one, magnetic field and the direction of the current. Okay, so according to Flemish left hand rule, where will now be the force produced? The force produced here, normally because we turned our hand, the force produced here will be RT what? Upward. Normally it's supposed to go down, right? It's going to go upward. The force produced here will be going upward, the force produced here will be going downward. Why? Because we reverse the direction of the North Pole and South Pole. Because we reverse the direction of the North Pole and South Pole. So the force produced here will be downward. The question is, the current is going down. If you look at Flemish left hand rule, if the current is going down, the force should go up. Right? If the current is going down, the force should go up. According to Flemish left hand rule. But remember, in that case, the North Pole should be here. The South Pole should be here. Normally it's from left to right. So once you change the polarity, the force that is supposed to go up here will now go down. The force that is supposed to go down here will go up. So that's why. Is that okay? That's why this is the direction of the... So this rotation will be what? Clockwise or anti-clockwise? This rotation will be clockwise. Because here will be pulled up, here will be pulled down, causing a clockwise rotation like this. Causing the coil to rotate like this. The coil will be rotating like this in a clockwise manner. So this is a clockwise rotation. Right? So clockwise rotation. The coil will rotate in a clockwise rotation. So you see how you have to break it down. If it's structural question, maybe it will be 4 marks. So you have to break it down in order to be able to get it correctly. Is that okay? So it's a clockwise rotation. You see? Clockwise rotation. So similar questions and more severe questions will be there. For generator, I think we've done that of generator. And even though we're going to do generator, that will be another class, okay? We in one of our videos we've handled generator before, but even if we need to revisit it, that will be another class. So we've come to the end of our today's class. Thank you for joining us.